Thank you very much. So last talk, I just start stating several theorems. So I think the main theorem is somehow existence of various various infinity functors. And today I want to explain what is infinity functor and some general method to construct such infinity functors. So let me recall which kind of infinity category we use. So this sigma is a Riemann surface, two-dimensional oriented manifold. Then the gauge theory thinks its object is just a three-manifold whose boundary is sigma together with some boundaries. And then you have these two such objects. Then you take this instanton Floer homology. So you have sigma, we have this y1 and y2. Then this is a kind of, first this chain complex is generator is a flat connections on this boundaries. And the boundary operator is something like ASD equations on y cross r. So this is one infinity category which I introduced last talk. And then there's another thing.
Sorry,
yeah.
When you consider Floer homology, you consider maps from some Riemann surface. Well, now, which do you fix Riemann surface or result does depend on the Riemann surface?
So this is a fixed Riemann surface, or better to say two manifolds.
Okay, but you introduce complex structure.
And for this, no, because this is purely topological. Okay. But of course, to define ASD equations, we need to fix Riemannian metrics. So, but Floer homology is independent of Riemannian metrics. So this is a kind of purely gauge theory things. And we have so we have this X omega is a symplectic manifold. Omega is closed to form whose top power is the volume form. And then you have this category. In this case, object is L. X, it's a Lagrangian emergence. Together with so yesterday's version we assume some monotonicity, but just I want to monotone. And you have B, some bounding quotient. That I need to explain later, but yeah. And then you have these two of them. Then the morphism, the chain complex is a G module whose generator is phi. This is the case L1 is not equal to L2. And in the case it is the same, it is just the homology of L. We assume that it's different, then it is transversal. And you have boundary operator, counting this, M1, and the composition is something polygons. So we have these two infinity categories. And something we want to first do is to construct some infinity functors. So suppose X is R of sigma, flat connections on sigma. Then then the first infinity functors we want to construct this Z of sigma to F of R sigma. So this is called the Floer functor. And another thing is something like you have this sigma 1, sigma 2, two Riemann surface. Then I want to write G, sigma 1, sigma 2 is a G of minus sigma 1 and sigma 2. Then the composition functor is something like a product to this sigma 1, sigma 3. So this is something called something which should be A infinity by functor. And there are something else on the symplectic side, but that I will soon go, correspondence functor. But before going that thing, I want to kind of first define what is infinity category, what is infinity functors, and some method how to define functors. So what is infinity category? C. It is first thing we have is set of objects. So this is a set. It's a small category. So the set is an object. And suppose we have two objects. Then this is C prime. This is a abelian group, maybe free abelian group. It is a set of morphisms. Then we have this map Mk, which I also introduce. Mk C prime to C prime. And this guy is by definition the sum over C0 Ck of tensor I Ci minus 1 Ci. And here this sum, so that C0 is C and Ck is C prime. So its element, I can just write. So you consider this C0 equals C, C1, blah, 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 Ck minus 1, and Ck is C prime, and you have this Xk, and you have X1, blah, blah, blah. Then the Mk is something defined, Mk X1, blah, 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 Mk. And that is an element from the morphism here. And in a simplest case, so when, today I start K is 1. And then in a simplest case, M1 is just a map from C prime to itself, and it's a boundary operator. And M2 is a composition. So and then the next relation is that this composition is not associative, but it's a kind of associative up to chain homotopy. This means that M2 X, M2 YZ plus minus M2 XYZ is M3 commutator of the M1 of XYZ. So this is the next of the infinity relations. It means that this M2 is associative modulo chain homotopy. And you can go higher. So this is the definition of infinity category. So now something I want to say is that you have these two infinity categories. Then there is a notion of infinity functor. This is a bit complicated. I just wrote down the formulas, and the actual construction is somewhat different. So this consists Fk to Bk C1 Cc prime to C2 Fc prime. So first of all, this F, maybe Fo, is a set theoretical object of the object of C1 to object of C2. So this set theoretical map, and also you have this higher map among the morphisms. So F1 is just between morphisms, and F2, F3, blah, blah, blah is the higher things. And the relation is something like this. Yeah, it's a bit complicated, but M of this F, X blah blah blah, F blah blah blah, F blah blah blah, sum is F blah blah blah, M, X blah blah blah, blah blah blah. I don't want to do so much in detail, but if you consider k input, and you split it into arbitrary way, and you apply f. And then if you apply m on the C2, that is equal to first apply m on C1 and just apply f. So that is the AMVT formula. And if you just take homology, then this is just the usual definition of AMVT of functor. This means that the composition is kind of commutative. Yeah. So now let me consider the problem. So what I want to do is just solve. Maybe this is main part. So at your Floer functor, it's just you have this gauge theory category, and you want to associate to this Lagrangian Floer category of this space of flat connections. So for spaces, object of this category is Y, whose boundary is sigma. Then what do we associate here is just called R of Y. This is a flat connection on Y. And this is something like, by restrictions, is a Lagrangian submanifold of R of sigma. So for object, it is somehow simple. And what we need to do is a morphism. And to cook up this functor directly is a bit issue. So I just want to do the following formulations. It's something like, I think, so-called Morita theory. Morita theory is something like this, right? If you have a ring, you have R1, R2 are rings. Then you have a ring homomorphism, associative ring homomorphism. Then it corresponds to something like a Bi module. What it means? So you have this ring homomorphism, then so you have a ring homomorphism F. Then you have this R2, R1, R2. What it means that this is a module, left R1 module and right R2 module, so that XA is just a F of A, X, and XB is XB. So this is called a Morita equivalence. And what's important is that here you have a tensor product. So you have this kind of, V R1, R2, W R2, R3. Then you have this tensor product. Better to say that it's a derived tensor product, but maybe let me simplify it like this. So this tensor product is actually R1, R3 module. And this process of tensor product corresponds to taking the composition of the ring homomorphism. So something we want to do is the following thing. So we want to have these two AMVT categories. So to construct these AMVT categories, we construct something called the Avt Bi Module. So what we do is just, first of all, we have this Avt Bi Module over J of sigma and this Lagrangian category. And of course, this is a bit cheating. So you have this only one, right? You have a ring homomorphism. You have this Bi module, but of course, not all Bi module correspond to ring homomorphism. So we have to show that the particular Bi module I will construct corresponds to some infinity functors. But the proof is in that two steps. So what is Avt Bi module? The V is the C1, C2, infinity Bi module. This means the following things. You have object C1 of C and C2 of C2. Then we obtain B C1, C2. this is some vector space, I don't know, Z module. Everything is Z over Z in this case. And then in general, we have this multiplication, and in this case, kind of most general case is that Bk C1, C1, C1 prime, tensor B, C1 prime, C2, tensor BL, C2, C2, C2 prime. So you have this kind of a byproduct, which goes to B, C1, C2 prime. So this is NKL. And this looks rather cumbersome, but what if N00 it goes from V C prime to itself. This is a boundary operator. And N10 is just a C C1 C1 prime tensor V C1 C2 goes to C1 C prime, yeah. So C1 C2. So this is the left multiplication. And in a similar way that this N01 is a right multiplication.
Is it the V in the...
B?
No, V in the target. C1 acts on V.
Oh, this is C2.
V.
No, this is B, yeah, B. Yes, you're right, yeah. And you have this N01. This is the right multiplication. And so on. And you have all higher in NKL, which satisfy some kind of infinity type relations. This is called Avt Bi Module. Then something we can say the following things. This is, I think, a kind of tautology. If you have an Avt Bi Module over C1, C2, then it induces an infinity functor from C1 to the category of right C2 modules. This is, I think, I mean, you don't, you forget this everything on infinity. You can just consider kind of bimodule over ring. You have a B, which is a R1, R2 module. Then you have a map from something like a category of R1 module to the category of R2 module.
Do you consider the right of the product?
This is right. C2 action is always right. So so you have this. So why this? You have this object C1 here. It gives B C1 dot, and if you change dot, it gives the right C2 module.
So my question is, when you take tensor product, it is derived tensor product?
Yes, it's derived tensor product.
Okay.
So composition corresponds to derived tensor product.
Okay.
So this is the construction. So first thing is that we find the Avt Bi module over these two infinity category. Then we obtain this infinity functor from G sigma to right this module. This is actually a DG category. Two right module you can say about the morphisms. Then there is something called the Yoneda functor. This is called the Yoneda functor. So what it is? So if you have any C, an infinity category, then you have from C to this category of, so there is an infinity functor from C to the category of right C module. And this is something, again, tautology. So if C is an object of this category, then you have this C prime go to C, CC prime. So this is the right C module. And and you can just use some infinity operation itself to cook up all these operations. And that is this Yoneda functor. And if you compare this, for example, in the case of if you replace MVT category to kind of abelian category or additive category, you can do the similar thing. It is just the usual Yoneda functor. And there is a theorem called A infinity Yoneda theorem. This means that this natural map is actually homotopy equivalence to the image. So we can define the notion of homotopy equivalence between infinity categories. It's a bit linguistic, I don't want to define it. And this Yoneda embedding is actually an embedding. Then the second step is the following things. So something you want to construct a functor from here to here. Then we have this guy using Bi modules. So you want to prove that there exists this rift. And to define this rift, because this is the embedding, you only need to show that for any object here, this image lies in the image of this functor. You don't see anything about the morphism, just the object. So these two steps is the one I want to construct. And this strategy is somehow we use for other construction of all these infinity functors we study in this series. So main thing is, so we need to prove two things. One is we need to construct this Bi module over this gauge theory category and this symplectic category. And then we show that the image is representable by this Yoneda embedding. This looks very much somehow idea of this category theory. So how to construct this infinity Bi module? Over this G sigma hook R sigma. So let me recall what we need. So first of all, this Y is an object. G sigma. This is a three manifold whose boundary is sigma. And then we need this Lagrangians. This is a Lagrangian submanifold. So something we need to do is the following things. So given such Y and given such L, we need to construct an abelian group. So this is a kind of Freer's chain group of Y and L. So this is a Z module. And we have this N00. We need to construct this N00, which is a chain complex. Actually, I omit 0, B. And then N10 is something like a Freer chain complex of Y1, Y2, tensor Freer chain complex Y2, L, which goes to Freer chain complex of Y1, L. I'm sorry. So, and there are many others, infinity many operations. And it should satisfy some compatibility, kind of infinity type relations. So we need to cook up this infinitely many operations plus infinitely many relations. So that's the task of this construction of this infinity Bi module. And so this Z module, I can explain what it is. So this guy is something like a pair of A, P, Z, A, P. And this pair, A, is a gauge equivalence classes. Of flat connection on Y. And So this L is a Lagrangian immersion, so you have this map from L to R of sigma. And P is an element of this L. And the condition is if you restrict A to sigma and it takes gauge equivalence classes, it is this I of P. This is I. So in a situation we have this. So this is what we given. So we have this three manifold. We have this Lagrangian submanifold. We consider a pair of flat connection on Y and a point of L, so that if we restrict this flat connection to the boundary, oh, maybe it is easier to hear. If we restrict the flat connection Y to sigma, it gives an element, this particular element P.
Is there needs to be L of Y, L tilde?
Where it is?
L tilde?
No, L tilde is L is a Lagrangian immersion. So it's a pair of L tilde and IL.
Oh, okay.
So that is the conditions. And in general, there are infinitely many such a pair, but if it's transversals, we can perturb it a bit so that it's transversal to get finitely many elements. So this is a free abelian group generated by this object. So that's first of this group. Then the next is this boundary operator. And this boundary, maybe this is the kind of most important part. So you have this two pair, AP and BQ. That is an element of this generator of this here. Then I want to define this N00, AP, BQ. This should be an integer. And N00, AP is a sum over BQ of these integers. Right? So this is somehow the way to define this. And the main thing is to define this integer. And this integer is defined as a kind of order of certain moduli space. So I want to introduce one moduli space. So this guy is an order counted with sign of certain moduli space. And I want to introduce this moduli space. So it is some kind of I introduce some differential equations, which is a mixture, which is kind of, in some part is Yang-Mills or ASD equations, and in some other part it is a Holomov curve equations. This moduli space is simply introduced by Lipinski, and actually I introduced somewhat related moduli space earlier, but we found that this Lipinski version is easier to construct, so work out. So we use this Lipinski's one. He do it in something like 2010, and it takes some time before kind of it's fully worked out. So now what it is. So we consider the following picture. So first of all, we consider this y. So y boundary y is sigma. So we cook up this y cross R. This is the four manifold with boundary and infinity. And the boundary is just a R cross sigma. And we consider, first of all, A is a connection on this y cross R. So I draw a picture here. You have this y here. So this is y cross R. And this line is the sigma cross R. And then we have another thing, so another domain. and we consider U it is on this domain, so it means that 0, 1 cross R to R of sigma. So this so A lives here. And U is a map here to R of sigma. So this is the two objects. And something I want to do is that, so first thing is that A satisfies this equation. This is the ASD equation. So A is this anti-self-general equations. This is exactly the equation Floer used to define Floer homology of cross-form manifold. Then next U is holomorphic. And I remark that this R of sigma is actually the projective algebraic variety. It is some moduli space of stable bundles over sigma. So it's has a complex structure. So here you have this holomorphic things, and probably the most kind of important condition is what is happening here. The condition is the following things. For any tau, we restrict A to 0, tau cross sigma. So any point here is a phi by the sigma. So you restrict A here, and this is flat. Moreover, so this is a flat connection. So we take its gauge equivalence classes. And that should be U0 tau. So U is a map from R sigma. So if you consider the point, this point, then U takes a value on the space of flat connections. And we require A is flat here, restriction of A is flat here, and it coincides with U. So you have some a bit strange thing. You have these two, which looks like a different object. There are connection here. There are map to the space of flat connections. And on the part it matches. We require this matching conditions. So that is kind of Lipinski's matching conditions, which is somehow important in this whole business. So you have these conditions. I mean, without any of this kind, it is hopeless to get any nice moduli space. And this way gives you some Fredholm theory.
So you consider product of sigma times R times interval, right?
So this is R, y times in R.
Yes.
And you just restrict here.
Yeah.
Boundary of y is sigma. So this neighborhood is something like this neighborhood somehow is a kind of -1, 0 cross sigma cross R. And then you have some condition here. Then you see that there is another boundary here, 0, 1. And we use L to fix boundary conditions. So it means that U1 tau is an element of L. Or better to say, it drifts to some L tilde. So this is a boundary conditions. And this space also has an end. So this is fourth, and this is fifth. Fifth is the following things. If you consider the limit, tau go to -infinity of A, y times tau, this goes A. So let me remind you that we have this. We start with two elements, AP and BQ. And A is a flat connection on y, and P is L tilde. And you take this plus minus infinity, minus infinity. Then next thing is U, limit tau go to minus infinity U T tau, and this is supposed to be P. So we in this limit, we have this A and P. This part goes flat connection A, and this part goes flat connection P. And you see that this assumption, this condition shows that it should match here. It means that the restriction of A to sigma is P. That is exactly the assumption we put here. And you take this plus infinity. Then this is B, and you take plus infinity. Then this is Q.
Kenji?
Yeah?
This implies the assumption about the restriction of A to sigma being P because of finite energy condition, which implies that or somehow, like, so as tau goes to infinity, you should say that, like, U is constant along 0, 1.
Yeah, so what finite energy implies that in some transversal cases, then there is some limit of this, in exponential order. And because of these conditions, it implies that A and P, restriction of A is P. So so I don't know all the conditions. So you have this pair of AST connections and map U, so that A is an anti-self dual, and U is holomorphic. And on this line, they matched in some nice way. And on this line, you go to L. And minus infinity and plus infinity, we have this asymptotic limit, A and B. That's rather complicated conditions, but it's somewhat natural conditions. And Lipinski introduced this moduli space, something like 2000. And he proved, basically he proved this several things. Most important thing is the compactifications and the removable singularity and regularity. For example, he proved that a weak solution of this guy is automatically smooth. And also there are some kind of removable singularity theorems. And if you know something about the removable singularity theorem in gauge theory or pseudo-harmonic curve business, then you know what is the removable singularity. If you consider any point on y cross R, and he assumes that A is defined outside of that point, and his energy of A is finite, then it implies that A extends to that point. That's Uhlenbeck's removable singularity theorem. And another thing is that you have a U here, you have some point here, and U is defined outside of that point, and the energy is finite. Then you extend to that point in a smooth sense. That is, I think, Gromov and also Uhlenbeck's removable singularity theorem. And what is most novel and something difficult is that you have any point here, and suppose you have this pair A and U, which is defined outside of this particular point on this bad line, and suppose some finiteness of the energy. Then I need to prove that it extends to this point in a smooth sense after gauge transformations. That is this mixed version of removable singularity theorem. That is proved. And I can say that we are working on SO3 bundle on sigma, whose Stiefel-Hoyteri class is non-trivial. And it seems that to prove this removable singularity theorem at this stage, we need this non-triviality assumptions. We can formulate the same problem for trivial bundles. And I believe removable singularity is correct, but I don't know how to prove it. So we think about it, how to prove this removable singularity, but we cannot prove it at this stage.
What is exactly the condition?
Pardon?
What is the assumed condition for the removable singularity?
W2 of E sigma is equal to fundamental class. There is no reducible connections. And in the case this point is a kind of reducible connections, then the analysis has some difficulty. So I don't know how to prove this Rainbow singularity.
But then you assume finite energy on both sides.
Yeah, finite energy, yes, under matching conditions. And so Lipinski proved it in some early years, and I think we try to make it easier to read. And something which is not written in Lipinski's paper is the so-called Fredholm theory. So the one main theorem is that this moduli space has a nice Fredholm theory. It means that in a generic situation, you have a smooth manifold for this moduli space. So that such a story is kind of, you have some kind of moduli space of nonlinear partial differential equations. And in a typical case like AC connections or pseudo-harmonic curve, we can use this moduli space to define, study Donaldson invariant or Floer homology or Gromf-Witte invariant. So individually, for this part and for this part, we have this kind of full set of the package on a moduli space of curves of blah, blah, blah. But this version is something like a hybrid. You have this matching line. So we need somehow generalize the whole story, regularity, Rainbow singularity, compactness, Fredholm theory to this kind of moduli spaces. That's the main part of this joint paper I wrote with Riccardo and Lipinski. And the Fredholm theory, we have kind of feeling, but kind of mostly Riccardo was very powerful, and he wrote very transparent proof and all of this basic package. So I believe this basic package is now well established. So we can safely say that this moduli space is kind of as good as the moduli space of harmonic curve or AC connections. So now we have also have this dimension formula. So the definition. So I want to say that the following thing. We want to define this N00 A P B Q, and this is a number of solutions of this equation with this boundary conditions counted with sign. And in the case, this index is 0. So we have a Fredholm theory, you can say about index. And we can consider the case index is 0, then this is the compactness theorem allows us to say a number. And there is some work about the orientations. It's somewhat non-trivial. But we have a kind of orientation in a case, at least there is a spin. Then we can define it's a sign. So we take the signs count and you get the number. And that is this coefficient of boundary operator. Then if you look at this, then this you can this proof. This guy is actually rather immediate. I mean, it's not immediate, but this is a kind of well-known kind of argument that Floer theory always use. So Floer proved this kind of things if there is no kind of harmonic curve cases. And also, there, in the case where there is no gauge theory part. So here, just this guy. Then the Floer proved this Floer homology boundary operator square is 0. And in this case, L is so in this case, suppose L is embedded. One can use this monotonicity to prove kind of avoid bad boundary. And here is immersed. There are some bad boundary, but this bounding cochain resolve this issue. That's a kind of due to F4 cube and Akaho-Joyce. And in the gauge theory side, you have a similar thing for the gauge theory Floer homology. And in our case, there is no reducible, so you can prove it. So that is this proof. So that's something like not so much novel. Once we cook up this full package of this moduli space, we can prove it. So now, the next thing. So next thing is something like maybe I think to explain both right and left module structure is a bit too much. So I want to explain left module structure. It is CF y prime. Maybe before going that I want to say something like this. So once we cook this, what we have this? We have the CF y L and its boundary operator. So you can say that the kernel divided by cokernel So let me write this HF is Y, L. So this is something like a Floer homology of 3 manifold with boundary with coefficient in Lagrangian submanifold. And this kind of thing is studied. This is probably equivalent, but something defined by Salomon and Wertheim. So they use slightly different moduli spaces, but they find this kind of Floer homology of 3 manifold with boundary. But actually, if in their formulation, it is harder to have a right module structure. But anyway, so now let me try to explain what is the left module structure. So something I want to explain is this kind. Two. Right? So we need to define this. So this is a left module structure. And the right module structure is similar, but so I just want to explain these particular things. So what one is this? So we have this y and y prime. So something we do is the following things. We first consider this domain. This is exactly the domain I draw here. And then, so we take this cross sigma. Then here arrow sigma. So you have this. So we have this domain, two-dimensional domain cross sigma. You have a 4 manifold. And you have this, this is y cross r. So this is r. So you have this y cross r. Then this boundary is actually sigma cross r. And the boundary of y cross r is also sigma cross r. So you can glue them together. And you take this y prime. So this is similar. You glue them. Then this is y prime cross r. So you glue them in this way here. So this to the boundary disappear. And at this infinity, what you have is that here you have this y connected to some sigma y prime. This goes to this end of this guy. So this is a picture on a 4-dimensional side. Then we have this another things. So this is another domain. You have this L. So what we do is the following things. So we have this big thing. So x and this. So x is something all here. This part is an x. So you have this x. And the boundary of x is actually this guy. It's a kind of r cross sigma. And you have 3 ends. One is something here, and one is something here, and one is something here. Then what we do is the following things. We have this A connection on x, and the U is again here. So now most of the conditions is basically similar. So first of all, this A is a self-equal connections, and U is a holomorphic, and 3 is that A restricted sigma cross tau is flat, and is flat, and its gauge equivalence classes is U0 tau, and then U1 tau is L, and 5 is somehow, when tau go to plus minus infinity, then A and U goes to P, no, AP or BQ. And so these conditions are very much similar to the definition of N00. And the last thing is this end. So then in the last end, which go to this way, A is asymptotic to some alpha, alpha is a flat connection on Y1, Y2, right? So this end is this sum of Y1 and Y2. So if we just go here, Y and Y prime, I'm sorry. So the picture here is that we have this pair A, P, and you have picture B, Q, and you have this picture R. So you have the three boundary condition at infinity. And what's kind of, this one is very usual Floer type boundary condition. You have a family of, you have AC connections on this product type end. So it goes to some flat connections. But this is a bit kind of new because you have a mixed end. You have this three manifold and the surface holomorphic map. So it's a pair goes to this AP and BQ. So this is somehow the equations. And you see that once we have this cook up this full package of the first cases, this case is very much similar.
Just there, when you said the restriction of A to Y tau, wouldn't it be to like Y hat in the
Where it is A Y tau sigma.
Oh, no, okay, yeah, sigma.
Sigma is the boundary of A.
Yeah, and then in condition 5, you mean
This is Y.
when you go to, but then when you go to minus infinity, it will.
Then it go to BQ, AP. So this connection goes to some flat connections on Y. That is A. And UT tau, independent of T, go to minus to P. That's the point of Lagrangians.
But that A that we drew down there, that's a connection on Y.
This is a connection on Y.
Okay,
And this is a point in L.
okay, so it's not on Y tau.
Yeah, I mean tau go to minus infinity.
Because there it says Y prime in the picture in the bottom.
Yeah, Y prime, sorry.
Oh, I see. So AP is an element of Floer chain complex Y prime L. BQ is a Floer chain complex Y L.
Okay.
So we get this moduli spaces, and you can see that almost regularity, Rainbow Singularity, compactness, Fredholm theory is very much a parallel to the case of N00. Then we count it. Count this solution. Then this is something like N10 alpha AP BQ. And then the definition N01 is just BQ of this number BQ. So this is N01. So what is N01 in this case? N10 in this case. Alpha moves this Floer's chain complex of Y prime. And this guy moves this Floer's chain complex Y prime L, and it goes to Floer chain complex Y L. So this is a correct map. And this gives a left module. And something I need to prove is that this is a kind of respect to boundary operator. But that's the kind of reasonable proof in the Floer theory. You see that you consider the case of one-dimensional moduli space, and then there are three, which is called sliding end. One goes to this infinity, the other goes to this infinity, the third one goes to this infinity. So you can prove that this is a kind of correct left module structures. And so then you can do the right module structure in a similar way. And In a case you have several y's, you have this kind of a bit more complicated spaces, and you work out of the family of Riemannian metrics, you get this bimodule structure. So that's the construction of the bimodule structures. And I mean, the picture is looks a bit cumbersome, but I mean, once you understand it, this is rather simple natural pictures. And the main work is just to work out the analytical details that this gives the correct things. So this construction gives the following. So this construction gives the following. We have the start Lagrange gauge theory things, and then you have this light module over this symplectic things. Then the next step is the following things. So the last step to construct this Avt Floer functor is that given y, the object. So let me write this Avt Floer hat. Then Avt Floer hat of y is in the image of this Yoneda embedding. Yoneda embedding is something like which goes from this guy. To but then if you see that there is a very natural candidate of this object which goes to this light module. So the thing we have to prove is that this guy. So this is I want to prove is the following thing. You this take and you take y, then this is the kind of homotopy equivalent to the R of y itself. So this may be Lagrangian submanifold of R of sigma. So if you prove this, then this guy is represented by this Lagrangian submanifold. Then using Yoneda lemma, we got this Avt Floer functor. Then this time is mostly up. I just want to write one formula how to prove it. So what is Yoneda? So let me take L any Lagrangian submanifold. Then this means the following things. So this guy, so left hand side is chain complex Floer homology with coefficient m y. On the right hand side is a Floer chain complex of R of sigma L, right? This is the right hand side. And I want to identify these two things. And something very easy to see is that the generator of these two are actually the same. Because the generator here is just an intersection of R of sigma and L. And that is actually exactly the same as this one. So as an abelian group, they are the same. So all I need to show is that they are chain homotopy equivalent. But actually not only that, because this is a kind of light module. So if you change L, you have this structure map of light actions. So you have to make it in a way compatible with light actions. But then we can just explicitly write the formulas as follows. The formula, so that's the end of my talk. The formula is following. We have a map from CF R sigma L to CF Y L. which maps to 1 to which maps x to n 1 x. And what is this n? N is the following map. We have the CF of y r sigma and the CF r sigma L CF y L, and here is a x, and then there is a 1 here. What is 1 here? So this is something like a degenerate case. Y r sigma, the generator is just an all element of r sigma, right? R y, I'm sorry. This is r y, I'm sorry. Yeah. Yeah. Sorry. This is r y. Everything is r y. So y and r y, for any flat collection y, this is a kind of element. So this is a kind of most support case. You have a positive dimensional manifold. In that case, you can take fundamental class of positive manifold. That is 1. And you plug in 1 here, and you multiply by x. You get an element here. That is the right multiplications. And since the time is up, I want to stop here. I just want to consider the fact that 1 is a generator. Then we can prove that this is actually an isomorphism. The reason is basically this guy is kind of defined by some moduli space. And there are some particular element of moduli space in this particular case. That is the case when A is a globally flat connections, U is a constant map. That gives this isomorphism. And there are higher order term, but the leading order term is isomorphism, so it's isomorphism. And by this particular formula, you can easily find that this is a right module isomorphism. So that is the proof that this is representable. So that gives this construction about the Floer conjecture. Thank you very much. I just run now.
Is it N10 or N? It's like the left module?
No, this is right module structure. It's something, I mean, I didn't define it, but it's something, you start from here. And then here, you have this L and L prime. So this is the right module structure. Yeah, I mean, this is kind of, the generator is RY fiber product RY. So it's RY itself. So its fundamental class has a meaning.
So if you want to show that to prove the original Floer conjecture, then you have to sort of show this functor is fully faithful or something like that?
Yeah, so I mean, that step is, I didn't, so we just find the constant functor, and I need to show that Floer homology, in this isomorphism Floer homology. That one can do in a similar way. But that's not the original form, it's a kind of SO3 versions. And the original form is trivial boundary cases. And for that, one difficulty is that I don't know how to prove this removable singularity.
I have a trivial question, I think. Why is it the same generator as the left-hand side?
Because this guy consists of a pair of A and P, so that the restriction of A to sigma is equal to P, right? But then this is the flat connection, this is P. So this is kind of tautology.
Thanks.
I mean, the Floer conjecture itself is something like if you consider generators, flat connections, then it's a coincide. That's tautology. That's the reason, one of the big reasons that Jan Floer conjectured it. But of course, the main thing is that how these boundary operators are related. So here, kind of impressive, there are several people like Wilhelm and Salomon. They try to kind of relate moduli space directly by some adiabatic argument. Here we use some kind of go around, constructing some mixed moduli spaces.
So I want to see if I understood correctly. You construct those mixed moduli spaces to avoid constructing the morphisms.
Yes, yeah, in a sense, so if you can know this adiabatic argument directly, you find that in some limit, to chain complex or something like become equivalent. But in place doing that, we have some moduli spaces. Yeah, so if you just look this formulas, the strategy, one use somewhere the inverse of Yoneda functor. And the proof of Yoneda lemma, infinite Yoneda lemma is somewhat a bit non-trivial. First, we construct this Yoneda functor, and then we want to show that. Then we prove that it is a Avt functor, and it is the isomorphism of the homology. Then, using some inductions, we can prove the homotopy inverse of this Yoneda functor. But the homotopy inverse of Yoneda functor is cooked up by some rather complicated inductions. And in principle, we can calculate it, but it's getting more and more complicated formulas. So if you want to see how this isomorphism goes more explicitly, then you need to see that this inverse of Yoneda functor somewhere. And that's very complicated formulas if you try to do it directly. So this way to use this Yoneda thing avoid that kind of complicated formulas.